Okie dokie. Yeah, you already got a short introduction. Just to recap, I'm Peter, this senior software engineer with the gray hair. My daily job, I try to be as much as possible with my hands in the dirt. With gray hair, that's always a bit a challenge, right? Because they expect you to do more managerial stuff and lead stuff, but I really fight hard to be able to code on a daily basis. You also see me often on stage. I'm also a trainer at Tib Academy, where I foremost train Kotlin. So I'm also a Kotlin certified trainer by JetBrains, where I help actually people in all stages of their Kotlin adoption, mostly server-side. So beginner, intermediate, but also advanced. When you look at my career, I started out with Java. About 10 years ago, moved over to Scala, and since quite a few years, do Kotlin. And throughout all these years, also right from scratch with Scala, I did stuff with reactive programming. Had a lot of headache in Scala, and eventually in Kotlin, I had this revelation of coroutines. And I think a big part of what I'm going to share today also you will see back in my career, and that I think finally we fit really the sweet spot. So I assume not all of you have done something with coroutines, so I think it's helpful to quickly recap why should you do something with basically reactive programming and later coroutines, and where is the headache? That's what this webinar proposes, so I think we need to have a good understanding where the headache is. And the example I will use throughout my presentation is what you see here. Very simple example where I have some endpoint in Spring Boot, store users. I fetch data from 2 endpoints, random avatar verify email, assume some remote blocking calls, do some validation. Eventually, I save my user in a database using, for instance, GPA. When I look at this particular example, it's very clean. There is no additional fuss about it. So you might think, why should you ever need something else? Well, if you put this particular piece of code under load, then you might see why I need something else. What I've done is I have created the exact same application here in Spring Boot with what you see here. And besides what you see on slides, what you also can do is you can add an artificial delay to the remote calls. So using this delay, I can kind of postpone the answer for the given amount of time. And we'll see why this is important later on. Then I can call my endpoint, of course. That's what I do here. And you see I get a response back. I also can time the response. That's what I do here. And then you see how much time it takes. And when you look closely, I have now a delay of 200 milliseconds. And we see that it takes about 400 plus something milliseconds. And that's kind of important to realize why. Well, kind of logical, right? Because we do 2 remote calls and a bit of overhead for storing my user in a database, adding up to about 400 milliseconds plus something. So far, so good. Now, the interesting thing comes. I put load on my system, and instead of having only 200 milliseconds delay, I now have a delay of 2 seconds. So I really increase the delay significantly. In a healthy system, I would expect that my average response time would be, what do you think? Always good to think. Well, you guessed it right. You expect 4 seconds plus something for storing user in database, right? That would be the ideal situation. And I do this, by the way, with 100 concurrent users and a total of 110 requests. So now this is busy to bombard my system. And here I get the response. And this is actually the important section. What you see is that the minimal response time, so the best one was 4 seconds plus something. So that's fine. But the average, as you can see, was 18 seconds. 18 seconds. Well, that's not a healthy system, right? To be fair, I have to kind of show you that to create this dramatic effect, I had to tweak things. I had to reduce the amount of threads I'm using here. But no matter how many threads you have, eventually when you have enough load, you always reach this particular point. So the question is then, what happened? So it's important to understand these kind of architectures to understand what happened. With the Tomcats, the server containers out there normally have a thread pool. And when the request comes in, it takes a thread out of the pool, uses the thread through the whole call chain. So we then call a remote service, we call our database. And whenever this thread is waiting, it just sits there and waits for a reply. When it gets a reply, it continues, which then eventually leads to returning response. What happens now if one of these resources, if these endpoints become slow? what we exactly mimicked with our 2 seconds, right? Well, then if you have a lot of load, what can happen is that your thread pool exhausts. There are no threads available for new requests because they're all waiting because they're doing something remote that takes a long time, which leads us to the very inconvenient situation where we cannot accept new requests. Well, this is kind of the best recipe for unhappy users, just not be responsive at all. And on top of that, what you also can re-leverage here is parallelism, right? So this model is inherently sequential, so using the parallel construct is kind of hard. That problem is not that new, right? About 10 years ago, you had this movement of reactive programming where they tried to come up with a solution for this particular problem. What you see here is basically a rewrite of what you see in the beginnings using WebFlux, bare-bone WebFlux with the monos. That does more or less the same, except for one thing, it does something in parallel. Can somebody see where the parallelism comes in here? Just type it in the Slack if you see the method that does the parallelism.
I can guess, but it's very well hidden.
Yeah, okay, exactly. Yeah, where is it?
A flat map?
Actually, it's one line above. It's zip.
Zip. All right.
Because you take two monos, right? Zipping meaning, yeah, you do them kind of in parallel, and then you collect both results in the flat map. And the flat map you need because we actually save another user, which is another mono, and you don't want to have monos on monos, so this is where the flat map comes in. And you see, that's already quite an issue, but more on that later. For now, we just focus on what happens if you put load on this code, right? So we're just looking at the result, not how we get there for a moment. So I have again my program here. Then I have here the reactor example. So this is the timed example. And you see that now we have, for single requests, already better performance because we only have 200 milliseconds plus something because you can do things in parallel. So that's already kind of a win, right? That's the win. And now, of course, we want to see what happens if I put this stuff on the loads with the same kind of configuration like on the left with 2 seconds delay, pushing 100 requests concurrently. And now we see that this is the result we want. So the min is 2 seconds. The average is now 2 seconds. That's what we would have expected in the prior example too, except, well, the prior example had 4 seconds because we couldn't do parallelism. Here we can do parallelism. And because of that, we expect an average of 2, which we get. So why do we get here a way better result? Also here, it's good to understand how these architectures work, so you can kind of reason about this much easier. So what's interesting with reactive programs is that they actually have less threads than the ones we see before. So they use less resources. You have about 1 thread per core instead of these 200 threads we had in the previous example. But the way they handle requests is very different. So when a request comes in, every request is taken up by a thread from this pool. But whenever you hit an I/O boundary, at least when it's non-blocking, then the thread does not just sit there, wait for reply. No, it goes back to the pool, takes on new work, and goes on. Once I get a reply, and the same thread or another thread is taken from the pool and continues processing. And the same is then happening for the database up to the point where eventually a thread will return the reply. So what happens now if a resource becomes slow, right? With the 2 seconds we mimicked. Well, not much happened, right? Because the threads that kind of take on our requests are still available. They're not blocked, waiting for something. And besides that, we also now can leverage parallelism. And these 2 factors together leaves us to happy users. There is one important thing you have to realize, which is the following. What you really must do with reactive programming is do everything in a non-blocking way. If you do something in a blocking way, then you get a deterioration of performance even much faster than in the third example, because we now have much less threads available. So if some of these precious threads are blocked, well, then we have a big issue. So you have to ensure that everything you do is non-blocking. However, sometimes you have a blocking library. So you have to interface with something that is blocking. The good news is in case you have this, you just have to ensure that you have a separate thread pool, it's often an IO pool, that facilitates these blocking calls. And I hope you figure that out before you're in production, right? Because should you be in production and you get these issues, then, well, you have a problem. So from a runtime perspective, we saw that the reactive really behaves perfectly. That's awesome. But is it the answer to all problems? The big issue is that reactive programming ties us very, very tightly to their abstractions. So you see, this code here is about monos. It's not about our business logic anymore. So monos dominate our whole code base, which actually means that our business intent is lost. And besides that, we also can now not use normal programming constructs anymore. For instance, I cannot throw an exception. I have to wrap them all the time in mono.error and so on. Besides that, it's also very easy to shoot yourself in the foot. I have a good article of a colleague of mine who kind of described 10 pitfalls. It's so easy to make things wrong. Like, for instance, forgetting to use a additional thread pool when you do blocking stuff, or call the dot block method on a mono, which you just can. And in unit test, that's fine, but on the load, you get the issues. And what's also important to really be very conscious of is, why do you embrace this reactive way of doing? It's because of these things: resource efficiency, little parallelism, and maybe reactive streams if you use them. So because of these kind of benefits, you sell your soul, so to say, to a toolkit that will really dominate your code base in a very nasty way. So we can say reactive programming does the job, yes, but accidental complexity is just tremendously high. It's too high.
Course.
And this,
we
yes?
have a couple of questions. I don't know if you probably will address them actually in your presentation, but maybe it's just a checkpoint. So there
Yeah,
is a question by Amit. Is there any thread listening for the reply from the external resource when we do this in reactive manner? What happens when we have to wait in real application with the real, external resource communication?
Yeah, so what you mean is actually when stuff is coming back here. So basically, such an arrow, right? When
Yeah,
one of these arrows here.
exactly.
Well, to be honest, I haven't really done that deep. I would expect it to be a single thread that kind of, because there's a callback involved here, right? So you put a callback, you offload your network layer. On the OS, actually, there everything is kind of blocking. You don't have actually asynchronous way of doing on that layer. So this callback is placed there, and once the callback replies, it must be picked up by something. So there must basically be a thread that picks it up and kind of signals to another thread, hey, there is a payload available for you, continue processing. Yeah.
Exactly. And
Cool.
another
Good question.
one, would we see similar numbers with reactive style with a thread count of 1, since we have a relatively low number of requests? I think it depends again.
That's correct. That actually depends on how many cores you have, right? When you only have one core, basically one thread should be enough. But when you have more cores, then you wouldn't leverage your infrastructure. And when your application is highly I/O bound, so actually the threading part with reactive gives you a lot of advantage when you're I/O bound rather than CPU bound, right? CPU bound means that I have a lot of cycles in my application using CPU for that. I/O bound means I just offload, and when I have to get something back, I do something, offload again. So when your application is highly I/O bound, then with one thread, you can do a tremendous amount of work. There's also many databases out there, like for instance, Redis, which is single-threaded. But because they only do I/O, that just works fine. But in an application, if you do some processing, maybe some crypto or well, some business logic you process, then with the single thread for many requests, probably, yeah, it wouldn't work that well. So you need a bit more than that. So I think a heuristic is about 1 or 2 threads per core. That's kind of a heuristic which gave good results. Yeah.
Good. And another one by Amit, in terms of comparison, probably would Vertex have the same issues as WebFlux?
Yeah, Vertex is an actor-based framework. I've done a lot of stuff with Akka, which is also an actor-based framework, which do not advise personally. I really don't advise use it because it's a tremendous amount of complexity based on the idea of message passing. You pass messages, you get messages back. I found, for instance, just seeing call stacks, following them, what's happened in your system, that's already really a very complex endeavor without a lot of correlation logging and so on. So it's message passing. It's not really that you use futures, but to really follow a certain code path is already very challenging. So you get similar issues as with Reactor. Not exactly the same, but similar ones. Okay. Yeah, I think the question we just mentioned here, we will talk about it. But let's continue. I think there's so many questions, but maybe just we get more bit into, get a bit more flesh, and then I think maybe also so many questions will also be answered. One of the answers is this one. So coroutines really can solve this problem in a very, very neat way. So what are coroutines? Well, if we look at a compute architecture, we see at the lowest level, there's our CPU, and the CPU is the real thing, right? This is where the work is happening. On top of that, your so-called kernel threads, and they fight for a time slice on a CPU. This is why you can do quite a lot of work with a single CPU, because when you have multiple threads, they all get a bit of work. So when you have a machine with one CPU, you get the illusion that you can do things in parallel, even though the CPU really can only do one thing at a time. And kernel threads are quite expensive, so you can have about 4,000 per gigabyte of memory. The JVM has platform threads, so the normal threads you probably know, and they're mapped one-to-one to kernel threads. The cool thing about coroutines is that's a layer on top of platform threads, which are very lightweight. So you can have about 2.4 million coroutines per gigabyte of memory. In the end, also coroutine needs to be executed by a thread, because whenever you want to have stuff done at JVM, you need a thread. There is no way around it. But a coroutine is not bound to a thread. So one thread can execute many coroutines, and the coroutine can be executed by many threads. Here I have an example of creating 100,000 threads. Sleep for 2 seconds. And this would be the counterpart with coroutines. What you cannot do with coroutines is simply create a coroutine like you can create threads. So there's no constructor which says new thread, new runnable, and then run something.start. No, you always need a builder method for that. And the builders we use here is runBlocking. More on this one later. That's an important one. In this particular example, the launch is conceptually really the same like thread. So here we create an asynchronous process. This is what we're doing here. And then we have actually the next kind of snippet, which is delay. And this is the mind-blowing difference between threads and coroutines. So delay suspends rather than like in thread sleeps and blocks the thread. So here, nothing will be blocked, whereas here we block. More on that in a minute. So my next question would be, what do you think happens in the first example, and what do you think happens in the second example? Maybe someone can type that. No one dares? Okay, then we will just try it out.
As usually, the answer is it depends.
In this case, that's the good news. It doesn't depend. Yeah, that's right. Depends on how much memory you have, right? So let's assume with 2 GB of memory, 2 GB of memory.
It actually depends on the Java version as well. I have checked that.
Definitely. Yeah. But I mean, the end result is more or less the same. In the first example, let's run it. So that's what you see here. You get this quite quickly, which is an out-of-memory error, right? Get out of memory about 8,000 threads I can spawn with 2 GB of memory, which is kind of aligned with my slides where I said I can have 4,000 threads per GB of memory. Then for fun, let's do the coroutine example. And we see there that, well, it's just a piece of cake, because we can have 2.4 million per gigabyte of memory. So that's the conclusion. At the core of this coroutines universe, we have these suspend functions, and suspend functions are just normal methods that take arguments, return types, but they get this special capability. You can pause them or suspend them and have them resumed at a later time without blocking anything. That's the cool thing about suspend methods. But they also have some constraints, suspend methods. So if we have a layered architecture, like you see here, controller, service, repository, client, what you cannot do is start out with a normal Kotlin method and then call a suspend method. That wouldn't simply not compile. What you can do is use runBlocking for that. And we'll talk about that later, because I see this happening very often in practice. And people are not always aware what they're actually doing. So we're going to look at that in detail. The way you should do it is start from the beginning with suspend method. And this is something your framework needs to support. That's not something you can kind of build in yourself. That's the framework that really takes something from the socket, has to ensure that right from the start we have such a context available to call a suspend method, which is a coroutine scope. You can call normal methods from suspend methods. That's fine. And should you do something blocking, then you have to ensure that you, again, like with the reacting example, need an additional thread pool. And this would be dispatchers IO. Also more on that in a minute. Now we're going to look at the most important ingredients of coroutines, because once you understand them, then I think you understand basically about 70–80% of coroutines. And that's great, right? These are these builder methods, and you see they have two building blocks, which is coroutine scope and coroutine context. So let's first look at the coroutine scope. In this example here, we create a thread. And what you see is, in case I want to kind of synchronize different asynchronous processes with threads, I have to join them manually, which is kind of very evil, because when you look at this example, we do two evil things. First, we sleep, which blocks the thread. And second, we join, which blocks another thread. So with a lot of blocking, we get our work done. In coroutines, because we have this coroutine scope, it looks more or less like as follows. That's a bit a fancy signature here. Suspend coroutine dot, probably the most fancy you think of in Kotlin. What this means is when I call runBlocking, what I get here implicitly as a receiver, so in the right terminology, is a coroutine scope. And this coroutine scope is my parent scope. Based on this parent scope, I can launch another coroutine, which once launched has another scope, which is a child scope. So what is the kind of idea behind those scopes? Well, every parent scope supervises the completion of the child scopes. So the parent always knows that its children, no matter how deep you nest them, no matter how process you spawn, it always knows whether they are completed or not. And this has this fancy term, structured concurrency. And because of that, we do not have to synchronize processes ourselves. It's kind of part of structured concurrency, which makes concurrency so much simpler to handle. It's really a wonderful thing, structured concurrency. So two benefits. First, we don't have to synchronize manually. And second, all this happens in a non-blocking fashion. That's really awesome about coroutines. Except for here now runBlocking, but let's just leave that aside. So within this block, there is no blocking going on. There's also another builder we will also use in our live coding session then, which is very similar to launch. So whenever you want to have a value back, you shouldn't use launch. Launch just spawns a process like a thread, and then it's kind of doing its own thing. It can't really give you a value back. If you want to have a value back, you should use async in combination with await. So this is what we see here. So once this delay has passed, then print line would be executed. And that's also very nice in Kotlin. So even though await is with another code block, the whole code block wouldn't be executed. Only once rabbit await would have a value available, then this block would be executed. Also here, without any manual synchronization, we just can do kind of sequential programming, whereas at the same time, we can do things in parallel. Okay, then the next building block is the coroutine context. And probably the most important part of a context is that it gives you access to the thread pool that will eventually execute a coroutine. And it is a bit more than that. We'll also see that in a minute, but I think that's the most important one. So another simple example here, I have runBlocking, then I launch two coroutines. And by default, I get this empty coroutine context. What does that mean, empty? Well, it means that it uses the thread that was calling this method. So if this would be a main method, it would be the main thread. So it would use the main thread to launch those coroutines. And then we do have these two delay calls. So question to you, how long do you think it takes to execute this method, more or less? And I know it depends, but more or less, right? The question is it 500 plus milliseconds or 1 plus second? That's actually the question. What do you think?
So it's less than a second or more than a second?
Yeah.
Well, to me, it seems that it's less than a second.
Yeah, I see 1 second plus. I see 500 milliseconds. So the battle is on, I would say. 500. Yeah, I think 500 is going to win. 500 plus is going to win. Very good. And that's correct. Why is that? Well, we only have one thread, but the thread that does stuff with coroutines is not blocked because we here use a suspend method. So delay is a suspend method. And that means that the thread that executes this code is never blocked. So it simply would launch, delay, it hits the suspension points. Okay, you suspend, it goes back to see, okay, what other coroutines I have to spawn. The second one would be spawned. Again, delay would be called. Something will be scheduled. Once the scheduled time has passed, the thread would again be taken to continue. And so we get about 500 plus seconds. Cool. What's really awesome about this coroutine context is something you're probably not very aware of, which is that it's propagated automatically. So once I define a coroutine context and I use launch to launch all coroutines or async, I automatically inherit the coroutine context from a parent. So I do not have to redefine it all over again. I can change it if I want, but by default, I simply inherit it. So now let's do a little twist here. Instead of using delay, we use sleep, which blocks a thread. So how long do you think it takes now?
Well, now it should be blocking because it's thread sleep. I think it takes more than 1 second.
Exactly. That's exactly the case. So we have, again, only one thread to handle all the coroutines. It would launch, but here it hits sleep and then it freezes. So it cannot launch a second coroutine. So it have to kind of wait till this one has been completed. Then it launches the next, again freezes. So this is why it takes 1 plus second. Well, can we solve this problem? Yeah.
Yeah, there is a very good question by Amit again. He is following. Where is the counting happening? Like, who counts those 500 milliseconds then?
Yeah, so it's actually not counting, it's scheduling. Maybe you've used a low-level scheduler in Java. You just say, after 1 second, I want this to happen. So this is basically how it works. So there is a scheduler that says, after 500 milliseconds, you have to do something. This is where things wake up. And indeed, there is also a thread that kind of checks the scheduler. Is there something to be done? And this is more or less how it's happening. Yeah, good question indeed. Nice. So the question is, if I have this blocking way of doing, can I fix that? Can I still get to the 500 plus milliseconds? Well, you can, using a dispatcher's I/O. And that's exactly the same what I showed in reactive programming, a separate thread pool for blocking operations. That's exactly this particular case here. Okay. So that was actually just a very short recap. And of course, today it's about Spring Boot. You want to quickly go into Spring Boot. And I chose to show you how you do coroutines the wrong way, because as I said, I see it happening so many times. I think it's valuable to know what happens when you embark on it in the wrong way. Kind of quick, we'll do that. And we again use this very first example we've seen in the beginnings. Now it might be that your PO comes to your desk and says, hey, this endpoint is so slow. Can you not kind of increase the speed of it? Then you think, okay, yeah, well, these two calls I could do in parallel, right? So let's try that. And maybe you've read a blog post about coroutines. Okay, let's try it out. This is what we're going to do now. A bit of live coding. So this is the piece of code. Then you probably heard of this thing which is called async. right? And what we also do, we're gonna log some information about what we're doing, exec this. This would be async, and then it says, hey, I need a coroutine scope. There is no coroutine scope. So then you might also read something about this runBlocking. Okay, let's use runBlocking because, well, then it compiles. The compiler is happy. Yeah, fine. Then, well, with async, I still need to do a wait, right? Because this is how these coroutines work. You also just seen that in the slides, and well, that seems like a good idea, right? So now I can call these things in parallel. Okay, interesting. I have the Spring Boot auto restart enabled. So let's call the thing like we did before. Say curl time blocking, and now we should get, with this delay of 200 milliseconds, something about below 200 milliseconds, right? That would be the idea. At column 1, so what happened? That's right, so that should be like that. And we see, hey, we don't get beneath the 400 milliseconds. Huh? I do things in parallel, but it doesn't do things in parallel. Why? Well, maybe you can answer the question yourself with what you just seen before. What we see here is that each time we execute this piece of code, we use the same thread, right? runBlocking has this empty coroutine context, which used the thread that was calling this particular method. And here we do some blocking remote calls. All these calls here, random avatar, are blocking calls. So the thread will be blocked right here, and so not being able to do the second async concurrently. What we get, and this is what I point out already now. So you see here, I generate some MDC. So this will be nicely be locked, the MDC. So that's what you see here, rec. And the MDC, that works kind of well. See, the MDC is everywhere the same. Then you, again, might have read the blog post, say, okay, when you have some problems with coroutines, it doesn't do parallel, simply use this dispatcher IO. Okay, let's do that and see what happens now. Spring Boot has restarted. Let's hit it again. Okay, you see, it's better. It's better. Yay! I got finally my parallelism. Wow. Okay, let's look at the code. But ooh, wait a minute. So I use different threads. You see, for one request, it's 5 and 4, but my MDC is gone. How is that? Well, if you think about it, it's logical because the MDC was on the calling thread, but I use different threads to execute those statements. So your MDC, which is on a thread local, is gone. There are some ways around it. Kotlin thinks about everything. It's really awesome. So you have this kind of MDC contact thing, which is a nice bridge between propagating state from a thread local to a coroutine. So that would bring my MDC back if you restart it. And so I do one call and let's see what the results. So you see I have my MDC back. But the real problem here is that even though that looks now awesome, we haven't solved our problem. If I again put load on the thing, like I did in the first example, I still have the same issue because my thread pool eventually might exhaust. So I do not get the performance I really want. At least that's what I predict right now. Let the result talk about it. And I think the result doesn't lie. So here it's min even 12 seconds. Maybe if I retried, it would be 2 probably, but the average is still, the way too high amount of number. This is what I call the very inefficient way of doing concurrency by simply throwing resources at it. This is how you do concurrency. More resources at it. Okay, so that was the bad way. By the way, there is even more evil to it. For instance, transactions. So you have transaction context on a thread local, which is also not propagated. You could do it yourself. There are no tools for that. But the problem is, if you do something with a database in these async calls, the way these frameworks work is that they're not really concurrent. They're not able to handle concurrent calls, for instance, for one database session. They're not just made for that. So if you do things concurrently in a single request with this one database session, you run into really nasty problems. So the point is, I wouldn't do that. And hopefully now you know why and can tell your colleagues, right? So how does the right way look like? This is what we want to know, of course. And the right way is basically use Spring WebFlux, which is more or less this stack. And we've seen that the complexity is just mind-boggling. But with coroutines on top of them, you get this. So complexity will drop from really nasty high to almost nothing. Of course, you need to know things about coroutines, but from a maintainability and a manageability point of view, it's really way, way better. So how do you address this? Very simple. You simply add these two dependencies on your class path, coroutines core, coroutines reactor. And then what you actually get is this. Reactor uses these monos. It's kind of a monad that models latency, right? It's like a completable future, which either gives you back an exception or value eventually, not right away. And what you get with coroutines that these monos literally disappear. They dissipate into thin air. And the only thing you kind of keep is the T. So you get the return tab is what you keep. And that makes your code so much more maintainable. But of course, that's what you can judge for yourself. Let's implement this in Spring Boot. So what we want to do first is do some remote call. And for that, we would use an asynchronous web client, an asynchronous REST client, sorry. In this particular case, it would be web client. So here below, I have my reactor example. That's what you see here. So this would be the service that calls the avatar. This would be my rewrite with coroutines. And I also can show this is so simple. It's really a piece of cake. You copy paste this, put it here. It's Java, by the way. So here it's Kotlin. We don't use pluses. Come on. We can use, of course, interpolation. And now just remove the mono. Remove the mono. Okay, you might think, okay, come on, guys, you cannot just remove the mono. There is some function to it. Well, the nice thing is, with a very simple trick, you can convert a mono to a suspend function. So what you have to do is make a suspend function. And you might think this is magic, but if you have more time, it's also what I do in my courses. It's really kind of a very simple trick to convert every asynchronous building block. So not only monos or future, every asynchronous block into coroutine. It's really simple. Okay, that's it. Of course, we want to make it a bit expression-oriented, remove all the nasty stuff. We do the same for our next service, that's the enrollment service, because it's so much fun, right, to improve that. And that's what we do here. Yes, remove the mono. We get a Boolean back. We await the body, which in this case is a string, and then we still need to convert it to a Boolean. Oh. And of course, it needs to be a suspend method, but IntelliJ just helps us with that. And now our signature has been healed, so to say, from the nasty complexity. That's it. So next, of course, we want to do stuff with our database. And here, well, there are some issues. GDBC is inherently blocking. It's a blocking driver. So when you use GDBC, you get exactly the same problem we've seen before. You get blocking code. And when you block coroutines, then you have a problem. So you have to use a different driver, which is R2DBC. R2DBC is available for all databases by now. For Oracle, it's only the latest version. And because you have to use different driver, you cannot just use all the standard frameworks out there. So if you use GPA or Hibernate, you cannot use at least the blocking version of Hibernate. There's also a reactive version of Hibernate if you want to do that. If you use Spring Data, I think it does a decent job. It's probably not as featurey as GPA, but in my experience and the application I've written, it's good enough. But that's something you have to be aware of. So let's see how we can also implement database logic. Here I have a Reactor repository. which uses this kind of syntax, which then will be translated to a SQL query. Let's copy paste this to Kotlin. Also here, bye mono, make it suspend, and that's it. And now you see actually two benefits here. First, we got rid of the mono, and second, I introduced nullability. Whereas here in the mono case, you actually don't know whether you can get the user back or not. You have to check with mono.isEmpty. Now our signature is richer, more type safe. So two benefits again, simpler and richer. And when you look at the tests, that's also really a wonderful thing. So if I want to test the thing, this is what you have to do in Reactive using these step verifiers. It's really a nasty abstraction. Recently, I used it in a slightly different setup and I got duplicate records. I really didn't know why. So it's something you have to learn. You have to learn a new API to only test or simply persist a user in the database. So let's see what you would have to write if you used a coroutine repository. So this would be our new user. Then we say user repository.save new user. And then we could say should not be null. And it says, hey, I'm a suspend method. But where is my suspend context? Well, here it's fine to use runBlocking because it's in a test. We don't have concurrency in tests. So here, for testing purposes, runBlocking is where it belongs for tests. That's why it's also so nicely marked blocking. And for our test to be aligned with the rest, that's what we want. If you use other testing frameworks, like for instance, CodeTest, you don't even have to do that. They already give you a coroutine scope, so it's even easier. So here we kind of test our find username method, find by username. We say new user dot username, and then, well, we check for the username, should not be null dot username, should be new user dot username. Okay, let's run this test. And now I also can debug decently, right? I can make a breakpoint. I could step into it. Here, debugging is a nightmare. And you see it's green. Yay. Okay. So finally, of course, you want to implement our controller and then see whether it performs the way it should perform, right? I mean, this is the kind of the end goal, what we want to achieve. So, and this is the reactor example we've seen before in our slides. So let's kind of rewrite this using coroutines. We have our avatar service, which now is a suspend method, right? That's fine. Then we have our, so this would be the avatar URL. Then we have our enrollment service, which also is now a suspend method. I get the email, pass my delay. This would be is valid email. And then I also do my check. And that's also beautiful here. Now I just can throw exceptions, right? I don't have to wrap stuff. I just would throw this Spring exception. Everything is fine. And else I again take my coroutine repository. So user repository say dot save. Take my user. Nice copy method available, which would give me the avatar URL. And off you go. And you see it complains because, well, it cannot just call a suspend function from a norm method. That's what I showed in the beginnings. That's not what you can do. So how do I do that? I simply make the suspend. And this is the awesome thing about Spring Boot. They implemented this, or they enabled endpoints, REST controllers to also be able to have a suspend method. So they ensure that from the start you get this coroutine scope in the, well, most efficient way you can think of. That's one of the really beautiful things that Spring Boot has embraced Kotlin and supports as a first-class citizen. I can tell you, Micronaut does that too. That works fine. Quarkus, unfortunately, well, does it, but it doesn't support, for instance, transactional. So these kind of things are not supported in Quarks. That's really a pity. And Spring Boot has really full-fledged support by now. It's quite recent. A few months, they have full-fledged support for every annotation you put in there. So also the security annotation, all the stuff there, simply supported. Okay, now what we don't have yet, of course, is our coroutine scope. for what we still want to do, of course, is do things in parallel. So we have to put the async stuff here. Then I need a coroutine scope. And what I can do is use this kind of builder method, coroutine scope, which gives me the scope, which is anyway there because I have a suspend method. Then I say await. I say is valid await. And that should be it. So what is it complaining about? Because I still need to convert it into a DTO, and everything is fine. So now for the final, I think time is up anyway. Let's see how this performs under load and so on. Okay, let's do a single request, coroutines. That would be a single request. Let's do the timed one. Home curl time. See, it's about 2 seconds something, so it does really do things in parallel with a delay of 200 milliseconds. And the ultimate test button coroutines, so the 2 seconds. So this was the reactor example. You see, the response times are, well, they're actually identical. So if I do it again, it will be fast or slow. It's really identical to reactor. It's not slower. The overhead is, there's actually no overhead. 2.6. Sometimes, yeah, sometimes one is faster than the other. Let's see if we can get it by just hitting the read. No, we know it now. It doesn't get faster. But I said that really depends on the run. So without additional overhead, you should get the exact same performance characteristics like with reactive programming. But then at the cost of actually knowing a bit of coroutines, but this is a programming model that really scales.
Nice. We have a question about R2DBC. Yeah. If it's actually a production ready. Do you know that?
I use it in production on a it's production ready. I said because for Oracle,
I checked. R2DBC is kind of it's not really like an implementation. Actually, depends on the database you use behind that. And I checked a couple of drivers, and they're all above 1.0 version, so they are kind of stable. I would expect them to be production ready.
Yeah, I said Oracle was the last one to support it, and in Oracle, I said it's a driver thing, so they only officially deliver it with the latest version. I think that's 21. But I think you also can use this for other versions because the database, they didn't adjust the database for that. It's just a driver thing, right? The database just remains the same.
Mm-hmm. There is a slightly longer version of a question regarding like here's like the context of the question, and the person is asking if there is actually a better way for doing this by now, like if they're like, because reactive hibernate is apparently is not really production ready. So do you have thoughts on this issue?
Yeah, so that's what I also mentioned in the beginning, which might be a bit disappointing in that sense. As said, Spring data is not as features as GPA. So if you have these relations that you're used to kind of to navigate them as you do in a annotated GPA approach, Spring data won't give you that. So the complexity you get there is the price you basically pay for using the asynchronous approach. And reactive hibernate, to my knowledge, I did a meetup beginning of this year. I saw that it's production ready. Even so, it is not. It's not a very convenient way of using it. It can also be because they have these low-level building blocks. They really heavily rely on these monos. There are some conversion method to coroutines, but it's not really an awesome experience. So,
I have a like just a foggy idea, I would say. I think this is the place where some architectural decisions need to come into play, because if you have an application that is written like over the years, it has accumulated certain, let's say, technical depth in terms of using this kind of technologies that are not really transferable to reactive programming. Then you start playing with the architecture. You keep the heavyweight interaction with the database that is blocking in that application that should be using, those APIs, and scale out by using, how you call it, backend for front end approach, having those reactive, fast microservices running in front of that heavy weight application, and then you might have multiple instances of that application running, and then the reactive microservice in front of those applications could handle the quick work, like quickly accessing the database using R2DBC for a smaller amount of work, and the heavyweight part of it could be offloaded to those real backend services or applications doing the interaction. But I think it's not an easy task to break apart like an old application like this. So it's still a lot of work, right? It's not something that comes just out of the box because I can apply a new technology or anything like that.
Yeah. Yeah, I agree with that. That's the way we also use it. Often applications are more read heavy than write heavy. So for writes, we use even blocking models for that because it's fine enough. We don't have to load there. But for the read part, we go reactive because they have much more load, which needs to scale, which needs to be highly available. We also use the CQRS pattern for that. So we have some sort of write part, replicate your read part. And yeah, for us, that works very well.
Exactly. All right. So are there any more questions? I think we still have quite a lot of people on the stream. Folks, what do you think about the content? Is there anything missing that you wanted to know? We briefly touched on Java Loom actually in the beginning of the session, and there was a
Mm-hmm.
question: what about
Mm-hmm.
virtual threads? Of course, we expected that. It just is not in the scope of this session today, but we were talking with Urs that we could run another session specifically on the virtual threads and coroutines and how do they relate. So, folks, don't be shy, ask more questions, and if not, there will be a section with the comments that you can leave your questions below. We will check them later and try to address in the further sessions. Okay, it seems that
Cool.
folks are happy,
Excellent.
and our time is up today. So thank you, Urs, for
5 o'clock.
coming. Yeah, 5 o'clock time.
Yeah.
Pencil drop. Let's go and have some tea.
Excellent. Yeah.
Thanks.
Yeah, there were some
Yeah.
other questions,
Thanks.
but yeah. Thanks a lot,
Thanks for
Anton,
coming.
also for giving me this opportunity and said a follow up with virtual threads and coroutines. That would be awesome. Of course, if the audience would consider this interesting. Yeah.
Nice.
Thanks.
All right,
Excellent.
folks. Thanks everybody for coming. Stay tuned for the updates. We're gonna have more sessions soon, and of course, we're gonna wait for Urs to come to our streams again. So goodbye, everybody, and have a
Bye
nice
bye.
Kotlin, by the way.
Thanks for joining. And indeed,